Welcome to the last session of this event. It gives me tremendous pleasure to introduce one of my colleagues from Microsoft Research, Victor Bahl. When I was asking around for things I should say to introduce Victor, and actually there was one thing that everyone said was a good word to describe Victor and his work, and that was awesome. But more formally, Victor runs the Mobility and Networking Research Group here at Microsoft, where he's a distinguished scientist. He's also an IEEE and ACM Fellow, and those institutions have also given him distinguished service awards for his work across his career. He's been at Microsoft, I think, for 18 years or so, and according to his website, he has one of the best jobs in the industry, which is perhaps why he's been here for so long. He can pursue his untethered research, shepherd brilliant researchers, and help shape the future of Microsoft and its long-term vision in the areas of networking. He's been hugely influential. His work and the work of his colleagues has been hugely influential in mobile computing, wireless systems, the cloud, and data centers. Just to pick on a couple of projects that he's worked on, which I think have had particular influence. He was involved in perhaps the first sort of indoor location system, Wi-Fi-based location system that really has spawned a huge amount of work in that area. And also his work on white spaces has been hugely influential, not just in the research community, but also in terms of government policy. And today he's talking to us about an area that he's very active on at the moment, which is the future of data centers and the cloud. So with no further ado, I'm going to hand over to Victor.
Thank you, Steve. Thanks. Okay. Thanks for being here. It's pretty late, and I'm actually surprised to even see that many people, but that's great. Hopefully, this will be entertaining for you. So I'm going to go very fast, but you don't have to stress over anything. It should be sort of fun. Now, let me just set it up. So Steve is right. I do think I have one of the best jobs, but part of this job requires me to ensure that there are no blind spots for the company, and also to sort of, to whatever extent I can, try to at least predict or think where things are moving so that we are all set up and ready to take advantage of that. So what I'm going to talk to you today about is something I am exceedingly passionate about. I actually deeply, deeply believe this is where we are going to be in a few years. And hopefully I'll make the case as I go along. And at the end of it, if I've done a good job. Say again? Oh. Okay, as my clicker just changed, I guess. All right. So hopefully at the end of the talk, you would know why I feel the way I do, and then maybe we can talk later if you have time to see if you disagree with it. All right. So let me start with this slide. I actually like this. This slide was introduced to me by Satya, who was here, but he left. And the point of this slide, as you can see, is we talk a lot about Moore's Law. We talk about how in silicon things have changed and perhaps not changed. But essentially, when you think about human beings, we are doing a lot more than we used to. We are context switching a lot. We are multiplexing. We are doing multiple things. We're looking at our phones, doing all this stuff. And the thing is, the demand for technology to be responsive to us has gone up exceedingly, right? The issue is that we have actually a lot of work that we have done in computer science and electrical engineering and the related mathematics and related fields that can be brought to bear to solve a lot of these problems, but we are not able to. So what we have today is good, but not great. And the thing is that we are struggling to sort of figure out, and there are some fundamental reasons why that is not happening, and I'll go through that. So let's start with this video. So this is, it's not overly sexy at this point, but many years ago when we did it, we sort of thought that what is happening here is, of course, the computers are recognizing people, they're recognizing what you're doing, and also recognizing where you are walking. So if you look at the left side of the screen, you see a little red dot, and that's saying where you are. And this is done all in vision with cameras. Wouldn't it be cool to say, if you had a system that you were wearing that would do all this stuff today? And my point was that, well, you can't do it with any of those systems that you have today, but you can certainly do it with a desktop quad core with lots of memory, lots of storage, and a massive amount of computes. So the technology is here. It's just not on our devices where we really need it, as opposed to here. And this is reality, because if you look into these are very recent headlines, and you see police officers across the world wearing cameras now. They're stitched onto their shirts, they're stitched onto their jackets, and they're using this. Now, of course, they're not doing as sophisticated a thing that I showed you. They're just literally recording the video so that later on, for later analysis, if something bad happens, so they can look at it. But we could do more, right? I mean, the fact is that the video is being taken. We just don't have the capability of processing. So wouldn't it be good if we could do some analysis and perhaps warn somebody? So if a police officer is looking in this direction and something is happening in his preview, but his attention is grabbed, maybe he could be told something bad is happening, so watch out. And we should be able to do that. But the good news, again, is that now we are starting to get to the point where we can do this video. So now in Microsoft itself, we have a project, Glimpse. We have been pursuing it. The idea is a little different from what you see, which is that in most of these things, like Google Glass, for example, and others, you think about augmented reality where you're wearing something and you can sort of augment this thing, augment the images you're seeing. In this case, you're wearing the camera and the system is analyzing the video, and you can then look at things that you may have missed. So in the middle, you'll see the video where this person looks at the video of the people that he missed when he was walking around, and the system has recognized that these are interesting events. It's interesting things for that person to see, so you can see what I missed. And this is not completely real time, but it's close to real time. So I want to sort of show you this thing. Now, move. So if you do, I'm from the systems community. I think a lot about how do you make this all real. I don't do the vision part, but necessarily try to make sure that it works in the systems. So if you look at the amount of processing that is needed, this is huge, right? DNNs is the state of art these days. And if you look at, for example, the accuracy is pretty good. I mean, it's very amazing. And I deliberately picked papers from other places to show that this was not about talking about Microsoft itself, although our own group has done similar things and has got similar accuracy numbers. But just generally speaking, the community has gone far enough to be able to create systems that can give you a very high level of accuracy. But look at the computation numbers and think about the systems that you wear, the phones that you have, the variables that you have, whether they can do this or not. Now, if I'll take another simple example of recognizing signs on the road as you're walking. And what you see is these numbers of doing this on a mobile, like current day mobile. In this case, it was a Samsung Galaxy Next, and on a server, which is a quad-core 3.6 gigahertz. And you can see on the leftmost column, you can see the magnitude of the difference between doing it on the mobile and doing it on the server. So as you look at these numbers through real implementation, it becomes clearer to you that we can actually do this, but we need more resources. We probably need to offload this stuff, right? We need to get the cloud we're talking about to do all this for us. And so that's we are headed. And also, besides the processing, the other number to look at is the battery here, the amount of energy that is used. And you can see about 21x times energy is less. If you could get it done, the cloud get it back to you in time, you would have saved that much energy, which means your system will last longer. It'll be much more useful to you for that time. Now, the question is, we need to get to, so hopefully I made the point to you so far that we need to offload. Okay, so we need to offload to a very resource-rich cloud. The question is, how long does it take to get to that cloud? Because you want to get there, process it, get the data back. These are some numbers that have been published. This is for 3G networks, and that is for 4G networks. And you can start seeing that the numbers are pretty big. And when I say big, you'll start to realize when I show you the impact of these numbers. I mean, for example, 70 milliseconds may not look like a lot, but has a massive effect on things. So these are the LTE numbers right here, and these are the 3G numbers. And you can see these are round trip of how long it'll take to get to the cloud. Now, this was done 2 years ago, like I said. I just did these numbers a day before I took a flight here. And so this is just a snapshot of what I saw. I did a trace route to one of the Google servers here, actually. And then you can sort of see right here, you can see it's about 120 milliseconds. And this is from another cloud provider. Again, going to the West Coast, you can see about 115 milliseconds. So those numbers that I showed you were actually more optimistic than what we are seeing today. And that was 2 years ago, those numbers. Actually, one was 4 years ago, the other one was 2 years ago. And today, just today, the numbers are not bad. And if you don't, not as good. If you don't believe me, you can actually, I have another point. So the other thing that happens is that these numbers get worse because our protocols are pretty bad, okay? So we are all familiar with TCP. I mean, at least the networking guys are. The devices guys also know about TCP. And you also know about TLS or SSL. And so if you look at this, there are so many round trips going on back and forth that it creates a huge problem. So on the horizontal axis, you see the RTT numbers. These are the numbers that I showed you earlier, right? And then this is the total impact of downloading an object because of those numbers. So when somebody says to you 50 milliseconds RTT, they really mean something like 530 milliseconds. So that's half a second. And now that starts to add up. So the protocols are not built in a way that can take advantage of that are fast, because the kinds of services we were building at the time we built these protocols were not the ones that we're building today. So this clearly shows that we have an issue here. And like I said, if you don't believe me, you can download this app from Microsoft's store. And this is called the Network Speed Test app, and you can try it. You can download it. I tried it here as well. I wanted to take a snapshot of it and show it to you. But you can try this app, and you can see that everything I'm saying about the numbers, the throughput, and so when you hear like your network gives you that much bandwidth, you can try this and see for yourself where you really are. All right, so we'll keep going. So what I want to do is I want to make this more real for you. And so what I mean by making it more real for you is that I want to tell you how it will have an effect on your real systems, these numbers that I've come up with, like 80 milliseconds or what have you, that I've shown you through measurements. So this is a typical processing pipeline of a game, okay? You don't really have to worry too much about it, except there's some client input when you're playing a game, and let's say, I made you to pound that I want to offload it. So you take the client input, you have some network delay here, then stuff happens, then the network delay, and you get decoded, and then you see the frame. So these numbers, so when I said 80 milliseconds, for example, so let's give it 40. These are the other numbers that add up. 16 milliseconds right here comes from the frame rate at which you are capturing. And then you have a little bit of processing here. So essentially, the 80 milliseconds moves up to 140 milliseconds. So now I'm going to show you, if you do it this way with the cloud, what would your experience be? And the point being that these millisecond numbers actually make a big difference. Okay. So I guess I have to click here. I'll do that. Okay, so here's an expert game player, and you can sort of see that when the number is just 5 milliseconds here, how does it feel? So watch his clicks and watch the punching there, right? You used to be able to see that. Now it's at 30 milliseconds. Now it's at 80 milliseconds. And you can see the difference. So that's why that little number had such a big effect. Now we had this player, so that was just to show you the difference. Now we had him play a game, okay? So and as you watch, he'll play this game, and when the delay is pretty minimal, then he's actually able to play a reasonable game, and he's going to shoot all the guys who are at him. So I don't know if there's sound here because it's kind of cool. Do we have sound with this? No? You can imagine, yeah. I have to tell you, I actually am not a gamer per se, but yeah, I got a kick out of this one too. So anyway, now he's at 30 milliseconds. The point to note is that whenever it becomes red, that means that this guy is shooting him out, like he's getting the blood and things. So he's getting very frustrated, actually. And you can see he's getting more and more being shot because he can't react fast enough. In fact, he's reacting fast. The game is not sort of responding as well. And now watch, so you can see that that's blood that he's hitting. And now he's at 80 milliseconds, so which is the number, the LTE sort of rule of thumb. You look at it about 70 to 80 milliseconds. And what you actually didn't see is what happens to him after this video is over. he will basically die here, I think. So the same gamer, he dies, and he just gets frustrated, gets up, and leaves the room. So really, you can't actually do cloud gaming if you have that kind of latency numbers. Okay, so let's move on. So, it's not just about me telling you that games or anything else. This is real dollar value. So when I talk to Microsoft executives, they are razor-like focused on trying to make money through their products. And so the big question is, hey, how much latency does it really matter? Does it actually have an effect on my bottom line? And the answer is it does. And so the way it's very hard to actually concretize that statement, but if you sort of start to look at some of these execs around the world who talk about it, who've done some studies, you can clearly read from this quote that if you're slow at something, your customers are going to walk away. And if they walk away because they're not getting the responsiveness out of frustration, then you've lost them. In fact, we have first-hand knowledge from products that we have built and our competitors have built that performance matters. It does matter in terms of just the user experience, and the performance has to do with how fast the computer is reacting to you. So this is just to sort of establish that there is a bottom line thing to all of this stuff that I'm talking about. Okay. All right. So hopefully by this point you see the 3 points, right, that I have up here. So offloading computing is necessary. I've demonstrated that to you by showing you how many computes you need to do simple things like recognition that you take for granted and we do a lot of work with, and if you want to do it in real time. Then I've also showed you that it takes time to get to the cloud, which can do it for you to get back. And I've also showed you that if you have the performance is poor, and poor I mean by in the game setting that I showed you, that if it's not, the computer is not reacting as fast as you do, then you just get fed up. And so the reality is that we have a latency problem, and that's an assertion that is not something that anybody would refute, I think, because the data just screams at us for that. All right, so now the question is, given that we have that, and given where we want to be, then the question is, how do you reduce this latency? And so we're going to just razor-like focus on reducing this latency. Now, I can't deal with complexity. That's a reality. That's a fact. And for me, I need to simplify things for me to be able to actually make sense of it. So I take this massive internet and I break it down into these 3 components. All right. So now we have the cloud. This is all the data centers that we talk about. Then we have a network that takes the cloud to some peering points. And so peering points are just points where different ISPs will match up. And then based on that, they will take the traffic, and you can have multiple ISPs matching up. Then that'll take you to the enterprises, that'll take you to organizations. It'll also take you to access networks like the wireless networks, the cellular networks, and all that, and that's how you connect. So this is really how, at the 50,000 feet level, the internet works. And so we're going to try to deal with each of these components separately. Now, I want to tell you about the Microsoft cloud, okay? Microsoft has invested a huge amount of money in the cloud, and it's doing superbly. If you actually read the literature, and it's true, Amazon is bigger. Microsoft started way after them, but it has been phenomenal, the growth of how fast how good our cloud is doing and how fast it's going. And these are some numbers that show that. Now, also, you may or may not know that they have invested up to $15 billion on our cloud infrastructure. And so at this point, as many as 5.1 tera transactions happened in just the month of March. These are absolutely totally fresh numbers that I have. 425 million active directory users. And so the point that I'm making here is that the scale of what I'm talking about is massive. Okay, it's nothing and there is no this is part of the reason why, for example, if you're in academia, which many of you are, it is a little bit difficult to do platform research in cloud, because the scale at which we are talking about these things, it's hard to get access to that kind of a scale. But nevertheless, it does create problems, but we have to do it. So the Microsoft cloud is huge and growing. Microsoft also has a massive network. This is not people don't know this very much. So for example, there's 1.4 million miles of fiber that we own in the US. Now imagine that. So when I showed you that picture and I said, I showed you the cloud and I showed you the network to the peering points, all that is owned by Microsoft, that whole network. And so when we run that network, what we are starting to see is because the cloud is going bigger, the amount of data that's going on this network is stressing the amount of data is stressing the infrastructure below it. Okay, so that obviously opens up opportunities. Now realize, like I said, Microsoft got into the cloud business a few years ago, and so at that time, there were many ISPs and many vendors like Cisco's and Juniper's, and that sort of managed the network and did their thing. But so the way we and most of the cloud vendors started to evolve was we would get all their hardware from everybody else, plug it together, buy our fiber or lease our fiber, and then run the network. But that network or that equipment was built for the internet. And the internet is a best effort network. A best effort network tries to do its thing from a stability point of view. But if you sort of think that now a company owns this entire network and it owns the entire equipment, there is no reason why you have to make it a best effort network. You can make it the best network, period, which provides you with the SLA, which provides you with the latencies that you want. So Microsoft researchers, for example, this is very hot work for us. We've just taken this head on. We have taken, just like the work that happened in the cloud, that if you're on a network, you would know you would appreciate what I'm saying. If you're not, then I'll say to you that most of the amazing amount of work that is going on in data centers happened because all these IT companies took their own destiny into their own hands and said, we are going to fix this thing, and they started to move and change the whole architecture. So the same thing is happening in the wide area now, which is that we're looking at the system, we are saying, hey, we're paying for this whole thing, we're going to make it the best system we possibly can. And like I said, I mean, it's huge. So this is, again, I'm digressing just a little bit, but I wanted to give you a flavor of the kinds of, I wanted to establish a little bit of credibility with the kind of things that I'm saying to you and what we have done in the past. So what this shows is, in research, we publish prolifically. So in fact, if you go to our group pages and you look at our papers, you will see papers, a whole lot of papers. The nice thing about these papers is that we are actually affecting and impacting all the product groups as well. So this timeline and these names mean nothing to you, but for the researchers who are in the audience and for the people in Microsoft, they mean a lot, because what they mean is these are the research projects that we did which got transferred into our product groups and are now real-world customers are using it and completely revamped the cloud. And the fact that we publish quite a bit, and there are companies that don't, they actually benefit directly from the work we do, and they are able to sort of, we are able to bring along everybody else. And so it works out very, very well. Now, I did tell you that, so this was the slide before that. I have no way of going back, so I sort of have to adapt. I don't know how you go back here, but I guess it doesn't matter. So what I wanted to tell you is just to give you a small little flavor of how we fix problems. So in the wide areas, as I mentioned to you, the way the world worked was you got this whole network here, you got a bunch of routers and switches, and you got a bunch of tools that manage this. And so when you bring it all together and you start to manage, you get all these different tools, and you got these human operators that have to deal with it, and they just clash with one another. And you can see that the scales we are talking about, that's going to create problems, that's what's going to create latency, and that's how the internet worked in the first place, because there was no entity that fixed it. So we look at that problem and say, that's screwy. Let's do it this way. Let's build something which we call the network state service. It sort of tries to build a sort of just like in operating systems and things, builds a driver-like model here, creates an API which is pretty static, and then on top of that, you start to write these protocols. It's a beautiful piece of software modularity, because now you can get people who are experts in traffic engineering, people who are experts in configuration and failure analysis, et cetera, to write this against this little level here, which controls all the level below. And now, boom, suddenly things become cleaner, and suddenly now you can offer these very strong SLAs. That's what, for example, SDN is. If you hear software-defined networking is revolutionizing, essentially that's what is happening. They're separating the control, they're separating the data plane, They're doing more programmability, and things are getting better. And that's why when I assert that we're going to fix that last piece, a few years from now, when we come and everything is deployed, you will have a data center, or you'll have latency fixed on that particular end. Now, remember, if you remember the old slide, again, I can't go back. So if you remember, so that was, we had the cloud. So my point is that in the cloud, we tended to fix a bunch of stuff. Latency is pretty damn good. From the cloud to the peering point, latency is going to get better and pretty good. But we still have the access network, and we still have the ISPs, and we still have to fix that latency. All right. So move. So the thing is that now we can do better, okay? So we can still, remember, bring you back to the talk. We wanted to bring these massive amount of resources directly to the user. So the question is, we really, as soon as the packets leave your device, we want to have control of them. And so we want to bring the cloud closer to you, okay? So what is the answer to that? The one answer to that is, hey, let's go build a lot of data centers around the world, all right? So if you do that, and in fact, it's not just us. I mean, everybody who's a cloud owner knows that fact. And they are doing that. They are building a massive amount of data set. So we too have about, they call it compute regions, about 19 compute regions that are shown in this color here. And as it turns out, they are more than any of the competitors that we have. And so there's a lot of money that is being invested. And these are called hyperscale networks, hyperscale clouds. And what I mean by hyperscale is that you can imagine a building which may have 200,000 servers in it. That's a huge building. And then if these servers have to connect to one another, and that's a huge task, not just to connect, and then they have to run efficiently at 90% utilization, and the networks between them have to run well, because if anything breaks at any given point, the whole system goes down and millions of dollars get affected by all the people who are betting on it. But nevertheless, these data centers are getting built around the world. So the question now is, are we done at that point? If you have a lot of these clouds built everywhere, if you have one in France and one whatever, a few in Europe, are we done? You don't have to go to the US. And so is this enough is the question. And the answer is it's not enough. It still isn't enough, because there's still latency even to these. And what I showed you are a lot of these data centers, and what I showed you, when I showed you the number from a couple days back, that was the numbers to these data centers. So we still haven't really fixed it. If we didn't have these regions, the number would be even higher. So then what do we do? So then the idea is, look, we can't build these. This is just too much money, both in CapEx, and it's too much money in OpEx, which is the operational cost for these things. So what we're going to do is we're going to build smaller clouds, very small clouds, and I'm going to call them micro DCs. If you heard Satya's talk, he called them Cloudlets. Actually, the whole notion of Cloudlets was invented by the both of us in Microsoft Research. He had visited, and we spent a day and a half talking about problems like that, and we came up with this notion of Cloudlets. And then he went, and he's been doing a tremendous amount of work, and we went and we started doing work as well, a little bit different kind. But anyway, so you build a lot of these micro data centers. They're not that expensive, and you spread them around the world. And you spread many, many of them around the world, okay? And what you're going to do is now you have taken a problem which is very wide and said, okay, from these micro data centers, I'm going to have a great network attaching myself to the back of the cloud. And so what I'm going to do is anytime any guy shows up, instead of taking him to the cloud, I'm actually going to take him to the micro data centers. And like I said, these micro data centers can be a rack of servers. It can be as small as one server. I mean, logically, you can actually, if you start thinking like that, if the whole computation pipeline is just a logic, then you can start to decide what that programming framework is and then accordingly make it happen that way. So now, what are these micro data centers? All right, so micro data centers is something you're actually very familiar with when you think about CDNs. And hopefully most of you know what CDN is, but if you don't, it's just content distribution networks. Akamai is an example of a CDN, and the idea there being that if you want some data, it's a static piece of data. Instead of going back to the cloud, you come to somewhere close by where it's cached, you pick it up from there, and you get better performance. So effectively, this is CDNs, and CDNs have been around for decades. So what are we doing here, okay? Now, what we are saying here is that this is more, micro data centers are now more than CDNs. They are CDNs, but now they're going to do computation as well. All right, so now, for example, we've already seen the advantages. If you do what is called proxying or SSL termination, the idea there being that when you start to hit the Microsoft cloud, you're going to hit this edge cloud, and then if you start to serve data from there, you already have saved yourself a tremendous amount of latency. So they are classic CDNs, but they do more. And what I'm going to do now is I'm going to try to focus on what that more is. All right. So there are many benefits of it. Okay. I could go on a huge talk. Each one of these actual bullet is a talk in itself because it's research and there are problems to be solved in each one of these things, and you go and talk about it. But this is the keynote, and I want to give you a flavor of where the world is headed, what is happening in the systems community, what is happening in the network community. And what I'm telling you here now is that there is a lot of good things that you can do if your computing infrastructure is very close by. So what I will do now is I will actually talk to you a little bit about some of these things, like battery saving. I'm going to show you how that is effective, and you will see the logic behind why I'm saying. I talked a little bit about high-end game streaming. There's other stuff, edge analytics and things like that. But so this is a lot of stuff. I recognize that. I don't intend to cover all of it, but I want to give you a sense that there's a lot here. Okay. So let's talk about object recognition, because in vision, mostly, most things can be broken again into something simpler. And I told you, my worldview is to think simply, and the way I think simply is in these boxes. And say, what are you doing when you're doing object recognition? You do some detection, you do alignment, do feature extraction, and then you do pattern matching. Okay, and you got some numbers here. Now, the interesting thing here is that on the horizontal axis is the time, on the vertical axis is the accuracy. These numbers n are the features extracted. And what this graph is telling me, and should tell you, is that the more features you extract, the better your accuracy gets. So if you extract, for example, 3,500 features, 3,600 features, your accuracy is about 83%. Now, you also note that you need time here. So you need time to do these sort of things, right? So any amount of time that you send on the network is wasted time, because that takes away from what you're going to do. And what is very interesting about this graph is that it's actually true for everything else too. So things like speech recognition, Cortana that you listen to, or Siri, or whatever, your favorite speech recognizer in spoken, or search that you do when you type in and you want the results to do, they are all affected by this. And they don't, in that case, they're maybe not features, but essentially they're doing essentially the same thing. So the time you're spending on the network is wasted time, and you don't want to spend any of your time there. And if you talk about DNNs, this is ongoing work in my group. And the accuracy number is not that high, but it'll get high. It's just, I just wanted to show you that, because for some of you who are purists may think, well, we don't do things like that anymore. We do it through DNNs. I want to show you is that it's the same deal. It's the graph looks same thing. Execution time, accuracy goes up as you move. And this is this little number. It tells you that you can improve the accuracy when you have more time. All right, so now what I'm going to show you is a video. I want you to look at this video carefully, because I'm going to ask you a question after this. And for those of you who have seen it, because I've given parts of this talks elsewhere, do not answer. Those of you who haven't, I want you to think about it and tell me what is it that I'm asking you for it. It'll also hopefully wake you up if you're sleeping here. Okay, here we go.
好好笑。
Really quiet here. Okay, so what is the difference between the two things? What was the difference between the two videos that I showed you? Sorry? That's right. So the answer is that in the first case, there were 7 people walking. In the other, and it recognized all 7 of them. In the second, it recognized, but recognized only 4 of them when the distance, because it couldn't compute fast enough. And so we had done it, we had created a micro DC which was close by, and we put the micro DC in the fast, and it actually, so you could see the latency did have an impact on that. All right, so it was actually pretty easy, but that's okay. Now I want to show you this one. You may have seen David's augmented virtual reality demo outside when he was wearing a headphone, I mean the head-mounted display, and you sort of saw what happens to latency. So what he does is he basically, I need to go back. What he's doing is, if you didn't see it, he's trying to cap the latency by doing speculative analysis. So what is going on is that he's predicting what the user will see, and he's processing that imaging and rendering it ahead of time, so that by the time the user moves, you actually have the image. And that's really trying to get rid of, or at least mitigate the disadvantages of latency. Now, so if you have the cloud, which is only a few milliseconds away, which we did, then you can see the actual difference between the two. So what we'll do is we'll run this. This video will look similar to the one that I played before, but here you will see it with the actual advances that we have had. So again, this is just to show what happens in terms of elapsed time when the network latency is there. So you can sort of see. And then when the MDC is closer, and you can offload all the stuff to the MDC and do the speculative stuff, you can start to see that the effect of the game is a lot better. Now we'll show him play the game. It's a different game than the one I showed you before. I was going to do the VR thing, but you guys had already seen it, so I decided to do this one instead. So it's, I don't know if you can see the two cases. So in one case, in this case, the cloud is sort of way nearer than in this case. Doing the same techniques though, and you can see that the difference between the two. Okay. Now let's talk about battery. That is very near and dear to a lot of you, I suspect, because you probably get frustrated that if you build variables, or that's one of the biggest problems that people face. How do you handle battery? So this is just to put perspective on those who don't think about battery. This is the number of years. This is how it's improved over time, and just to sort of be dramatic, that if you compare how the CPU is improved versus how the battery is improved, you can see there's a substantial difference. And the bad news is that there is really no silver bullet. It's not like somebody's going to build a battery, because the more energy you put in a little device, you actually create a bomb. So so it's just difficult. So how are we going to solve this battery problem? Well, what we're going to do is I'm going to tell you a little story. And I'm going to tell you a story that should be interesting. So here's what your smartphone is doing, all right? So what your smartphone is doing is, when you have some data transfer, it goes up. These numbers are from Verizon from 2012. It goes up to about 1.6 watts. It sends it. Then it comes down a little bit, and then waits for a little time, and then it goes down and goes to sleep. Now, you look at this number, and you say, that's pretty crappy. Why the heck is it awake? Why don't we actually bring it all the way down? Right? I mean, why waste? Because you're wasting a lot of energy right here, right? So here are some of the numbers. So it basically consumes 1.5 watts when it's active, and about 1.1 watt when it's inactive, before it actually goes to sleep. Well, so here's the story behind this thing. So, yeah, how did we get here? Many years ago, when iPhone first started, I don't know how many of you remember this incident. In New York, the iPhones they were very popular, and they brought down the network, okay? And so these headlines are from those days. So I think you can see the date, September 2nd, 2009, in 2009. And as you can see, people were like really unhappy. AT&T took a lot of blame for their networks not being up to speed and not being able to handle this. Now, what happened? What happened is that iPhone guys, who are the IT industry, just like us, they thought logically, the way I was presenting it to you, said, well, you have data, you transmit the data, and then you bring it down, and then you relax, because you have no data, so why waste the energy? That's what they did. Well, it turns out that the whole telco industry came from a circuit switch background, and the way they worked the situation was that if you made a connection, they would create reservation along the path and reserve all kinds of resources for you. And then when you didn't have to do it, they would bring the resources down, and so the path would be closed. Well, when you were doing this, so what was happening was resources were being set, resources were being brought down. Now, anybody who is in our industry understands that data is bursty. And the way our transactions happen, there's a bunch of transactions and there's silence, there's a bunch of transactions, there's silence, and we do a lot of that. Now, what that is doing to the back end is it's adding tremendous amount of signaling traffic, right? It's going up and down, up and down, up and down, and their systems could not handle so much signaling traffic, so they just went down, completely went down, and no connection happened. So they quickly realized what was going on because they saw this massive signaling traffic come up. And so what they said was that, wait a second, you can't do that, okay? What you're going to do is you can bring it down a little bit, but only as down as you can maintain the connection with us. And then, if for 9 seconds, if you have nothing to send, then we will relieve our resources and you can actually bring it down. So now, if you're doing this transaction, for every transaction you do, you're now wasting energy doing nothing, essentially. You're paying the penalty for the back end of the system, okay? So if you actually do the math, it's really simple. 1.6 watts high times whatever speed up you get, which is through because you might have some speed up, let's not get into that. And then plus 1 watts times 9 seconds, so 10.6 joules of energy being spent for every transaction that is happening. Now, if you do some more math and you say, well, I have 20 network transfers per hour, which is nothing. If you think about the number of transactions you do, that's way more than that. You basically are and you're using this cell. The cell capacity has become slightly better. And if you could get away with doing, you could just bring it down, you would have saved 26% of the battery. Now, with all the stuff that is going on in the battery world, trying to improve the density, we can save battery just by this kind of optimization on our systems. And then to make it even more dramatic, if you look at the horizontal axis, if you add the number of transactions, you start to see how much amount of battery you can save. You can save 75% of the battery usage. I mean, suddenly your smartphone, which was going dead in a few hours, can, if it was, all this was done properly, could survive longer. And so what that means is the way you would then achieve this is, I'm sorry, I went a little ahead. The way you would achieve it is you would, I'll go back here. The way you would achieve it is you will put one of these micro DCs at the base station. And then what the micro DC is going to serve, it's going to allow you to get your signal down. It'll suppress your signal, will not send the signal to the rest of the network, and then do the waiting that the rest of the network wants, and then after 9 seconds, if it doesn't get any signal from you, we'll release that signal so resources can be brought down, and boom, you've gotten your savings. So you're really, from your perspective, or from the network perspective, you're down operating at this mode, but the network is seeing that you're up at the high level, and so you've saved yourself some battery. So that will give you some drastic improvements if you brought computing to the edge of the network. So hopefully that was, I can't actually sense the audience, whether you guys are like with me still or kind of sleeping or what the heck's going on. So it would be good to. All right, okay. Well, you're just, that's just nice of Jeanette, but thank you so much. Thanks. Okay, so with that encouragement, I'll keep going. All right, so all right. So then let's talk about bandwidth. We talked about, and I started to talk about this thing. There are some fundamentals to systems, right? There's energy is a fundamental to a system. Latency is a fundamental to a system. Bandwidth is a fundamental to a system. And these are perpetual things that we have to keep fixing. So let's take an example of a wireless surveillance video. Now, I was in London for my sabbatical, and I found out that there were 1.5 million cameras in London. And I thought to myself, that's amazing, and that's also crazy, because if you've got 1.5 million feeds coming, who the heck is looking at those things? And so everything happens after the fact. If something bad happens, there's a terrorist bomb or somebody gets lost, they go back and look at the video and then try to analyze what happened. And I thought, hey, that doesn't seem like the smart thing to do. Maybe the smart thing to do is, could we somehow build a system that can alert me in real time if something interesting is happening? And that thing is coming from the fact that I came from the networking background. And in networking, same sort of thing happens. There are thousands of components that are across the network. And whenever something goes over a certain threshold, a red alert happens to the operator. And then the operator is overwhelmed by what we call as a sea of reds. And so we have worked in the past trying to reduce that sea of reds to just the reds that matter. And so with that mentality, when I looked at the camera, I wanted the same thing. 1.5 million video feeds coming. I only want to look at the ones that are interesting to me. And so let me see what the vision technology gives me. Can I build a system like that? So we said, okay, let's start with a wireless surveillance system. We will put a lot of videos across the rooms and things, and we'll watch it. Now the problem was we wanted to do it over wireless, and the problem is I can't actually, there's not enough bandwidth in the wireless system for me to sustain so many cameras at the same time. So then I am now compelled to build a system that will do some intelligence at the edge. All right, so the observation was that when things were happening, there's a lot of data, but really the interesting data is not as much. So I really am looking for interesting data. So what are you going to do in this case? You are going to bring the computing to the edge, right? You can't do it in the camera. You got to do it in some server that is sitting right next to the edge, and then you're going to decide whether that's good or not, and then you're going to use the bandwidth on the background. All right, so this is a video showing the system in progress now. The system is more sophisticated than what I'm showing you here, but nevertheless, I just wanted to make the point that we had a video sitting here, and you saw that most of the time there's nothing happening, so why stream the damn video? So what are you going to do? Sorry about the damn, okay? So as you can see, this is what is being sent back. And then you can see this is very jerky, and of course, because we are only sending back only a few frames. And it turns out less than 10% of the frame captured were objects of interest. Now, there's a lot of work going on. For example, there was some work that from Stanford and from MSR on scene analysis, where you can look at the scene and say if the scene is interesting or not. All of that can now be utilized if you do edge computing in this manner and build wireless systems. Now, that work was done in collaboration. I said, I was in sabbatical. I actually worked at UCL, so I don't know if Kyle is here somewhere. So yeah, there he is. So he was a collaborator in that. So this other piece of work I started doing right here in Paris. I was also here about 5 weeks, and I was thinking about, hey, wouldn't it be cool? I wanted to have fun at the time, so I was thinking about fun things to do, and one of the fun things I thought was, hey, isn't it cool that if you're driving around, if you could build the next generation of ways, right? So if you want to park instead of going to a garage, you can sort of say, hey, is there a street parking close by? And how would I do that? So, well, people have cameras. If they put the camera in front and they start to analyze the radio in the road, can I get the thing? So this is what is going on here. And this was also done in collaboration with Kyle here and Giovanni. Giovanni's here too, right there. And so that's Giovanni's student. He's going to get in the car, and I don't know how to operate these things. Okay, go back. And so you can see, he gets in the car here, and he puts his camera, the smartphone here, and he starts to drive. And he starts to detect the car. And what the goals here for us is to find empty spots. And so eventually he's going to find he doesn't have any spot available. I mean, there's a spot, so he can sort of say to a service in the cloud that a possible spot is, and somebody else says there's a parking spot around me somewhere, and the cloud comes back and tells you where the spot is. Of course, again, what we're showing you, the smartphone is not able to do that level of detection. So we actually have to have a computer in the car which is doing this thing. So that in itself is sort of a micro DC. Again, think continuum of the clouds, right? That is happening. So that was another one of those apps. So now, I mean, this is a research audience. I have to leave you with at least a couple of questions. But if you've been thinking and if you're buying into things that I'm saying, there are many, many research problems here. But let me just give you a little bit of a sense of a couple of problems. So one problem is you want to offload things, but you can't offload everything because your car, your variables, your phone, they have sensors in them. And you can, of course, you need to have some code that is sitting there. So for those of you who are software designers and things, you will immediately recognize what I'm asking, which is saying, what part of the codes are you going to offload to the cloud or the micro DCs, and what part of it are you going to run here? And of course, you're not going to make this you're not going to stress the application programmer about doing this. So you have to do whatever you do with minimum programmer effort, because the guy who's writing these applications is not a PhD, he's not, possibly not even a master's student. He's just a programmer. So the system itself underneath has to figure this out, okay? So what to offload, and then you also have to decide whether offloading makes sense, all right? So there have been research, I mean, there are papers out there, but I think it's still a very open problem. So for example, even from Microsoft, we had a system called Maui in which we offload methods, okay, the methods. And I'll say a few more words about it, just again to whet your appetite as to how to do it. Intel had this thing called CloudCone, in which they did it in threads, but essentially they were just migrating VMs. And in fact, if you look at Satya's work on Cloudlets, he also talks about VMs and VM synthesis and VM migrations and things like that. And then, of course, the Odyssey works. But all of these systems, the one thing common that is they have a profiler and they have a solver. And I'll give you a sense of what that is. So a profiler is something that'll take a lot of input. So for example, it'll take a call graph for your method. It'll take how much time it takes to execute, which you can figure out in offline. What is the state size for each of the method? It'll take how much CPU cycles, how much energy is left. This is something it can sense. And then this is in real time. It has figured out what the network latency is, what the bandwidth is, and what kind of network you're attached to. I am going fast. I recognize that. So again, I have to keep saying, I just want to give you a little flavor of it. So in the call graph, then you sort of annotate it by saying, oh, it takes 45 nanojoules or whatever, and then about 30 milliseconds to execute, and about 10 kilobytes of state that needs to be transferred if you do that. Now, once you've got the system set up like that, now, again, not to impress you, but to give you a sense that there is science behind everything I'm saying, and I just wanted to give you the flavor. And also, last night at dinner, somebody said to me, a great talk will have at least one equation in it. So here's my equation. And you know who you are. And you can raise your hand if you want to. But anyway, here we go. So what this is doing is it's basically saying, here's the energy saved if you pass it to the cloud. Here's the cost of the offload, because you've got some energy that is being consumed in sending it. And what you have to do is you have to take the execution time plus the time to offload, and you have to sort of make sure that that's within the bound that you have. And based on that, you will decide whether a particular method will get transferred onto the cloud or the micro DCs, or whether it'll stay. Okay? So that's how Maui deals with it. But as I said, when I've given this talk in the past, which was just specifically on Maui, there were folks who came back and said, why don't you try it this way, or why don't you try it this way? And I sort of wanted to say to you, yes, I actually recognize that there may be other interesting ways of doing this as well. And so there's something to think about as you look forward to some of these things. All right, I should also point out that there are people, I was in the audience, Rajesh, I saw Rajesh. His thesis was on cyber forging, so the amount of work that has been done in this space, there have been people who have thought leaders in this space who have done a bunch of work. So his thesis was on this as well. Here's another interesting problem that I think is interesting, and that relates directly to this IoT thing that you keep hearing about or you are interested in doing. And I think of it as a buzzword, but I think nevertheless it is an architecture one has to think about. For example, the camera thing that I showed you is sort of an IoT network. And so what is happening there, in an IoT system, you've got all these sensors that are giving you some data. It's coming to the edge, or it's coming to your cloud. Now, you're not going to bring everything to the cloud. That doesn't make sense. So what you're going to do is you're going to put something on the edge and bring it to that edge and do whatever computation you want to do or aggregate and then bring it back, right? So architecturally thinking, you now have these computes that are going on in different sides. Now, the question is, if you think about systems like MapReduce or Hadoop and SD inside of Cosmos, which is a Microsoft system, you think that from a programming perspective, how are you going to issue, for example, queries? And where are these queries going to run? Are they going to bring all the data back into the cloud and run it? Or they're going to partition themselves and run some on the edge and some here? And that itself is an optimization problem, because now you have to say, the queries could be such that there are so many of them, and so it might be even better just to bring the data in here in the center and then run it. Or you might want the data may be so much that you don't want to run it. And there may be other constraints as well. So that then leads to doing something which we call Geo Distributed Analytics. And you have to figure out what is the best way to do it. So here's some of the. I pretty much said what I've written here, so I won't go over it, and we don't have as much time. So and then there are a couple papers that we just published, and you can sort of read those papers. It'll set up the problem for you, and then you can go at it. Essentially, as I said, you can sort of, for example, move the data if and only if the cumulative shuffle volumes of the query exceeds the data size, sort of what I said. And then look at this and sort of see, okay, how would you design a system like that, or how would you make progress on a system like that? Because these systems are going to become important. They are going to be the next version of the big data systems that you're talking about. They are going to be the kind that are going to affect the Internet of Things system, and that's how you're going to see the world. All right. Now, like I said, there are a whole lot of things. I have given you just a few of these. I talked about battery. I talked about bandwidth. I've talked about latency. I talked about new services. There are things that excite some of the product group guys. And I know there are people here, Dina in particular, who has asked questions like, how do you manage this thing? All right, that's a serious problem. How do you manage it? I mean, of course, I don't have the time to kind of go into it because these edges are sitting in other people's networks as well, and you're sort of trying to manage the whole system holistically. How are you going to do that properly? That's a serious research problem. Then our product groups sort of are very interested in this denial of service problem, because when you're being attacked, if you are at the edges, if you can detect the attack at the edge, you can cut off that arm and you're done, right? So you can have to see how you work through that. And so, and then reduce the load in the DCs. DCs, if you're doing more stuff on the edge, the DCs can do more. So there's a lot of platform issues that one can really take on and do, and we are taking on, but we're going to require a lot of the research community to take on as well. And of course, from a perspective of, a lot of your build devices or are interested in building new applications, you're looking at a world where you can now do the really sexy applications, because now, and you can deploy them because now, hopefully, you will have a computing resource that is close to you, that it knows, and you can think of it just like you think of the cloud. All right, a few words about deployment. How is this going to all work out? Okay, so let me tell you how wireless networks are architected. The wireless networks that are sitting here in pretty much every part of the world is like this. You've got all these access points, and you've got a wireless switch in the background. The wireless switch is manipulating and managing these access points. And then, of course, you have all this other stuff that is sitting here, the DNS, DHCP, you've got some global authenticator, here's the internet, and that's how it works. Very simple and straightforward. Well, if you want a cloud micro DCs, all you need to do is put a server rack or a few servers and attach it right next to where the wireless switch is, and boom, you suddenly have a cloud, which is close to your thing. You're done. At that point, infrastructurally, you have it. So the point being, it's not that difficult to get these things deployed. Of course, there are business things that we have to worry about, but technically, they're not hard. You might talk about cellular networks. The busy slide. The point of this slide is that in cell networks, the new thing that is happening is they're looking at the larger capacity, so they go into these small cell. Small cells, conceptually, if you think about it, it's kind of like Wi-Fi again. All right, so you've got these smaller cells, and you've got these smaller cells. So what you do is you put your micro DC right next to one of those things, and boom, you suddenly have a cloud close by. And in fact, we have done it. These are some numbers in our own lab. We've deployed it. It all works. It's all good. Now, we started this work in 2009. That was the first paper we wrote. But as I looked around, I started to see that it is a wave. It is. I mean, I told you when I started by saying the world is going to change, and I'm very excited. And I think I know how it's headed. So here it is. You start to see Akamai, which is the predominant vendor for these CDNs. And lo and behold, this morning, as I was doing a search, and this is from this morning, I found the word Cloudlets in there, which is no different than micro DCs or Cloudlets that we conceived of. And as you go and start looking at all the things they're doing computing on the edge. Okay? You look at Intel, they're doing the same thing. You listen to the chief scientist of there, he says local clouds are essential on the backbone of the network. And he puts a little device here, and you can see it's computing here. Somebody from Hawaii uses the word Cloudlets on the base station. Okay? Then you go further, and then you start to see, you see this thing called Liquid Networks from Nokia Networks, and you say, this is a software stack that sits on the base station. It says base station application architecture. That's crazy, because we never thought that the base station would actually have some software sitting on it, which will actually do some service. Right? So they're selling this. They're actually starting to do this. And then you look further and you start to see, wow, they've gotten the standards involved now. They're talking about mobile edge computing in collaboration with IBM, Intel, Vodafone, Hawaii, and all the other stuff. You look at academia. If you've heard this term fog computing from Cisco, it's nothing else but what I've said. It's exactly this. It's just call it fog computing, and they show the stack. It's the same thing. You look further in academia, he says, mobile edge cloud for video streaming. It's all over. You start to look at papers. There are lots of papers now, both from MSR and others, which clearly demonstrate the advantage of doing it this way. And of course, like I said, we publish. I just put the citation here, not as to sort of tap ourselves in the back here, but to tell you the amount of uptake that has happened on these ideas of moving forward. So this is my last slide, and I want to say the way I view the world and the way I think the world is evolving, and where you will have these mega data centers, and they will be there'll be only a few companies in the world that can afford to provide that. But guess what? You're going to have a lot of these things, and they all have to work in harmony, and we all have to work together. Now, I don't want to be explicit about how this will evolve in terms of the company, but with a little bit of thinking, you can see there is a massive amount of business opportunity here for people. There is a massive amount of research opportunity in this new world itself. All right? So then I'll leave you with this thought. Why should you care about any of this stuff? Well, like I said, latency does matter for all the cool stuff that we want to do and we talk about in this conference and everywhere else. We need to have these massive resources. We need to build systems that can dynamically partition one another. We are looking at sort of this infrastructure which is changing, and you can yourself now build, you can have a micro DC in your lab, and you can start working on it. You don't have to worry so much about being in the cloud. And of course, you can start the deployment. And we are really happy to work with you on this. We are really happy to work with you from the research perspective of it. We are really happy to work with you on thinking about the business aspect of it. We are really happy to work with you on trying to give you a technology, whatever we have, that can sort of speed up this process, because I think that's going to make it independent of Microsoft, independent of any other company. It's just going to make everything cool for everybody. So at that point, I will say thank you. I have a thank you slide. Actually, I can say in French, merci. That's it.